Good afternoon, everyone. Welcome to Valongo Seminars. My name is Jessi, and I'm one of the organizers of the seminars. I also have the help of Douglas Brambilla, Ariana Cortese, and Aline Novaes in the organization. And today we have the great pleasure of having with us Professor Jessi Cisewski-Kehe. So Jessi is an assistant professor in the Department of Statistics at the University of Wisconsin-Madison, and she completed her PhD in statistics at the University of North Carolina at Chapel Hill, then spent time at Carnegie Mellon University and Yale University. Jessi, thank you very much for accepting our invitation. It's a great pleasure to have you here to talk about such an important theme in astronomy that serves basically for everyone who is working with big data. So thank you very much for accepting our invitation. Welcome, and you can feel free to start whenever you're ready.
All right, great. Thank you so much, Luan, for the invitation and for the nice welcome. Indeed, let me actually, I think I just put the wrong thing in full screen. So let's see, I want to go. Oops. I've somehow lost my. Okay, I'm gonna have to stop sharing for a second.
Okay.
And let's see. Sorry for the delay, everyone. Let me hit share screen. Share screen, and I'm gonna select. Oops. I just cannot seem to get out of this. Let's see. I wonder if I'm going to have to actually leave. Oh, okay. Let me try doing this. Can you all see the?
Not yet.
Okay. Sorry. This is all my fault. Luan had everything set up for me, and then I just messed it up. Okay, so.
It happens.
Oops. All right, so let me hit this. I want to go here. For some reason, Luan, it's just the StreamYard's not letting me get out of the full screen.
Oh.
I think I can. Okay, I got it.
Great.
There we go. Okay. Sorry, everyone. I'll try to talk faster to make up this lost time. Click the screen. It's like, this is really crazy. Everything was so nicely set up, and now it's your browser has blocked your screen. Click the screen icon on your address bar to allow access. Okay. Connection secure. Okay. Man, this is crazy. Okay, share screen. There we go. Okay, now it's at least appearing. Allow. Okay, can you see this?
Yes. So.
Oh, okay. Okay, so now let me actually try to get this in full screen. Okay, I think we're good to go.
Yeah,
again,
we're good. You're good to go, Jessi.
Okay,
Thanks.
And again, sorry everyone for that delay. That was completely my fault. But yeah, like I said, Luan, thank you for the invitation. I'm going to be talking today about just kind of generally what is astrostatistics. I'm going to give some background on the field of astrostatistics, and then I'm going to go through a few examples of some of my astrostatistics research. I'll do a little bit more detail of the first two topics, and then assuming there's time, I'll just have a very brief introduction to what approximate Bayesian computation is, which may be useful for some of you in your research. And then I'll have just one slide concluding remarks. I did want to show, this is an Institute of Mathematical Statistics bulletin on statistics and astronomy. And if you can see it, the date's from March 2009. And this is when I was a PhD student. And it was actually this bulletin that first made me aware of the field of astrostatistics. And it got me, I was very excited about it. I knew that after I finished my PhD, I wanted to get into this, what I consider a very exciting field. All right, so first, what is astrostatistics? Some of you may already be doing astrostatistics work and you know what it is, but if I describe astrostatistics, I usually will say it's statistics for astronomical applications, but really it can be lots of different things. It's research at the intersection of astronomy and statistics, of course, but also astroparticle physics, astrophysics, computer science, cosmology, data science, machine learning, solar physics, and the list can go on. And so it's so what I tend to do in astrostatistics is methodological development. But there are certainly different dimensions that one can work on. It can be methodological development. It can be applying new statistical methods that were developed maybe for a different application to an astronomy application. But it's a very broad field, and if you work in astronomy, I'm sure there could be places where some newer statistical methods may end up being useful for you with your work. So I just wanted to also draw your attention to some astrostatistics organizations that you may be interested in getting involved in. So there's this Cosmos Statistics Initiative, or COIN, which is a really great organization. They develop and run these different residence programs, which brings researchers from all over the world in different disciplines together for a week to work on some very specific projects. And there are other things going on within COIN, so I'd recommend checking that out. So this is a Astroinformatics Association, but there's definitely still ties to astrostatistics. And then there's the International Astrostatistics Association, which is another international organization where if you're involved in astrostatistics work, you might want to get connected to that. And then we have the International Statistical Institute has a group in Astrostat. The International Astronomical Union also has an astroinformatics and astrostatistics group. And then the American Astronomical Society and the American Statistical Association both have Astrostat and/or astroinformatics special groups that are focused in these areas. And there are likely other astrostatistics organizations around that I'm just not familiar with. But these are some good ones to check out if you're interested in getting involved in some of the more broader astrostatistics activities. And then here are some astrostatistics resources. This first one, I'd highly recommend bookmarking if you're involved in astrostatistics work. It's the Astrostatistics and Astroinformatics Portal, ASAIP, and it's run at Penn State. Eric Feigelson, an astronomer at Penn State, has been maintaining it. And you can see that it links to recent papers. There are other resources. It lists organizations, articles, forums, meetings. I believe there are there's a place where maybe even I think job postings in the area are posted, and so it's a good resource that's quite broad. And then there are a number of astrostatistics related conferences that happen. Some at some fixed interval, maybe every other year, every 5 years. And so my first big step into astrostatistics was actually attending one of these statistical challenges and modern astronomy conferences, and which was at Penn State. It was in 2011. It started by Eric Feigelson and Jogesh Babu. So Jogesh is a statistician at Penn State, and they ran their first conference on the SCMA in 1991. And so I'm not sure how much further back the term astrostatistics goes, but I know that Eric Feigelson and Jogesh Babu have been just foundational in getting together the astrostatistics community due to these conferences, and also with their own research. And they so also, Feigelson and Babu wrote this this textbook, which you may find useful. It has a bunch of statistical methods, and it uses R, which is a very popular computing environment that that statisticians use. And so what can be nice about R is that if you want to use a new statistical method that was, let's say, developed by statisticians rather than astronomers. I know astronomers do a lot of method development, but when statisticians develop methods, a large portion of them end up using R. So you might be able to get an R package to more easily apply to your data set. And so the Statistical Challenges in Modern Astronomy Conference, it's going to be run this summer, June 7th through the 10th, and it's going to be virtual. So so it makes it easy if you're interested to attend, because you don't actually have to make your way to Pennsylvania to attend this year. It's just going to be virtual, so that could be a good way to see what's going on these days in astrostatistical research. And then next year in 2022, the plan is to have it in person, assuming travel, et cetera, is safe. They also run at Penn State, the Center for Astrostatistics, a summer school in statistics for astronomers. And so this year it's also going to be virtual. And so you can see the information will be the beginning of June, and you can email talk if you'd like to get more information about that. Okay, so that was my kind of brief overview of astrostatistics. Hopefully I gave you some directions if you want more information where you can go. But now we'll get into some of my astrostat work. These projects that I'll speak of are things that I've been a part of. So I don't think this is all that there is to astrostatistics. It's far broader than what I'm about to discuss with you. So with this, I am going to talk about some aspects of the large-scale structure of the universe. As I'm sure you're all aware, this is a simulated universe from the Millennium simulation in the backdrop. And so what we'd like to do, or what we're trying to do with this particular project I'm going to discuss, is find statistically significant holes in the universe. So what do I mean by that? You're probably familiar with trying to find cosmological voids, right? The lower density regions in the universe. There are a number of different approaches that people use to try to identify voids. But what we were trying to do is use some tools from this topological data analysis field in order to find voids. And also, just because of the nature of the framework, we're also able to capture a new type of structure, which we call filament loops. Okay, so we have the two-dimensional, I should say I'll call it the two homology group generators, which would capture voids. And I'm going to explain what I mean by these homology group generators. And the one homology group generators capture these filament loops, which, if you imagine, it's just tracing out cycles in the filaments. If you can see my cursor here, I'm tracing one out. But if you follow a filament around and eventually it connects back with itself, that's what I mean by a filament loop. Okay, so I'm going to first talk a bit about topological data analysis, and then I'll go back to the application of the large-scale structure of the universe. I do want to point out also that, so if you work in astrostatistics, you'll find that some of the methods that you develop for applications in astronomy also can apply to other areas. And so with this kind of spatially complex data like the large-scale structure, you can find similar sort of complicated kind of web-like structures in biology. And this, what we see on the right, is an image of a human fibrin network. Fibrin is just the protein structure that forms when your blood's clotting. And so if we were, there are different things one might be interested in analyzing with this sort of web-like structure, but similar sort of techniques can be used across both. Okay, so what is topological data analysis? Well, what I work with in TDA is persistent homology. And persistent homology is something I will explain shortly, but we're going to begin first with homology. But before I even get into homology, I just want to say the general idea with TDA is you have some data set and you want to get, maybe you want to understand the shape information or the topology of what's present in your data. So we go from a data set to a topological summary to, with those topological summaries, we can do things like just visualization, trying to understand complex data, what the features are. Might develop inference methods, hypothesis testing, for example, or prediction methods using these topological summaries. Okay, so what is homology? Well, homology really is just a matter of counting holes. So counting the holes in your data, and we keep track of them using these Betty numbers. So beta 0 is representing Betty 0, and that's just counting how many components. So these would be like what I'll just refer to as the zero homology group generators. They would be like clusters. Connected components are like clusters, so they're groups. So we probably wouldn't really think of those as holes, but that would be a zero-dimensional hole. And then beta 1 is representing Betty 1, and that's counting the number of loops, and that's going to be related to the filament loops that I mentioned. And then beta 2 is representing the number of voids, and so those are the two homology group generators. So if we look at this collection of shapes here, we can see that this green loop just has one loop and one connected component. This kind of cloud puff here has one connected component, but there's no loop, there's no hole in it. And so this loop with a slash through it has one connected component because everything's all connected. But then we have two loops, right? We have the loop on kind of like the lower left and the loop on the upper right. Similarly, with the set of glasses frames, we have one connected component and two loops. And then finally, for this torus, assuming that it's empty, we have one connected component because it's all just one piece. We have one void because the interior, as I said, is empty. But then we actually have two loops here because we have the loop that goes around that middle loop, the middle empty space of the donut, like the donut hole. And then we also have the loop that goes around kind of the shape or the side of the donut, kind of outlining the void that's present. Okay, and then if we look at all of these together, we can see that we have 1, 2, 3, 4, 5 connected components, and then 7 loops, and then just one void that's present. Okay, so we're counting holes with homology, and so that works with just objects. We can just look at it and do that. Here's another example. We have the loop. But when we're working with data, we don't have a nice smooth manifold, right? We have points often, or maybe a function that could be a bit choppy. But in this case, we just have a sampling of points on the loop, and we might say that there's a loop there. It looks like they were sampled on a loop, but just given the data, we don't actually have a loop. We have 15 connected components and 0 loops. And then if we move on to a real data set, like a simulation, let's say, of the universe, if we want to try to start counting the loops, we would stop quickly because it would not be very fun and there would just be too many loops for us to try to find, which is what brings us to persistent homology, which allows us to compute the homology of a data set across multiple scales. And so it's this multi-scale aspect that allows us to take a data set that has, let's say, points or a lot of points and get a picture of the homology of those data sets. Okay, so how do we do that? Well, to go from, let's just say, a set of points as a data set, we have to add a particular filtration. In this case, imagine each of these disks has a data point at the center. And so our filtration parameter is going to be based on the size of the disk. And so at first, the disk is 0, which is just the data points. And as we saw previously, we had 15 connected components. And then as we grow these balls, as we grow the disks, eventually they become connected. And so at this point, with a radius of 0.45, we see that all the points are actually connected because the balls are intersecting And so let's say that means they're connected now, but a loop hasn't formed. There's still a gap, and so it's not closed yet. But at a radius of 0.48, it does close off. And so now we have the birth of a loop. And so with persistent homology, we describe the birth of a loop, and that happens at a radius of, so with our filtration parameter equaling 0.48. And then if we continue to grow the loops, these balls, the loop that we had that was there closes off, and that happens at a radius of 0.92. So the persistence or lifetime of the loop that was present is the difference between the two, and that is 0.44. Okay, so we end up plotting the birth and death on what's called a persistence diagram. And so here's a different data set where we have 3 noisy loops and its corresponding persistence diagram, where the black circles are indicating the 0 homology group generators, and the red triangles are indicating the connected components. They're indicating the loops that are present. So the red triangles are loops, and the black circles are the connected components. And so we have the birth on the horizontal axis here and the death on the vertical axis. And the persistence ends up being then the difference between the death and birth. And so the further the points are from the diagonal, the higher their persistence is. And sometimes instead you see this plotted as what's called a persistence barcode. Same information, it's just instead of a point, the bars are indicating the persistence. Okay. So that was dealing with points, but sometimes we have data that are functions, or another case is where we have data that are points, but we turn it into a function to kind of smooth out maybe some outliers or some noise that's present. And so we can do a similar sort of persistence diagram instead using a function where if we'd have our filtration parameter kind of start at, let's say, the minimum of the function. You could also consider starting at the maximum, but let's say we start at the minimum of the function and increase our filtration parameter, which is the threshold. And at some point we hit a bump here. And so we end up looking at the lower level sets of the case where so the lower level set of from the function as the threshold increases. And so at this point, you see this red dashed line, that's indicating the birth of our first connected component. The green line indicates the birth of the second connected component. And as the threshold continues up, we see that at some point, these two connected components become joined together because their lower level sets get connected when we hit this kind of local maximum. And so that brings us to the death of this particular connected component. And then we continue to increase the threshold and we hit another bump, and then eventually everything becomes connected. Okay, so the difference with the functional data is we now have a threshold and we look at either lower or upper level sets. And so we can do this with 2D data or higher. Suppose this was our data set and that we turned it into a function. And so this function is just using a distance, a particular type of smooth distance function. So where there are more observations, the value of the function is smaller. And so if we start at the lowest value of this function and increase our threshold to, let's say, 0.05, right? So that's somewhere here on this color bar. We get a collection of connected components, right? So each little blob is its own connected component, and that's going to be indicated by the points on the persistence diagram. And I'm just going to kind of flip through this, where as we increase the threshold, we'll start to see loops forming. And so in this case, this particular loop was closed off, and we see that's indicating the birth of this one loop on the persistence diagram. And then another loop forms, and then the third loop forms, and then all the kind of black regions here are now connected because we see this little connection between the top two loops. And so now we're left with one connected component, and then we just have two loops present, and then the loops eventually close off. And all of this then is captured in our persistence diagram. So the persistence diagram gives us the multi-scale homology of our data set. And so so we don't just get the homology of our data. To do that, we'd have to somehow know what particular threshold to fix our data at. But instead of just fixing the threshold, fixing the scale, we're able to get this nice multi-scale picture. Okay, so now back to the application. So we use persistent homology as a tool here to help us find holes in the universe. So the data in these images are simulated using an approximation to Voronoi foam. And you can see in this middle one, the kind of colored regions are where we found cosmological voids. And here on the right, we just pointed out one of the filament loops that were found. But we didn't just want to find these structures, we wanted to assign statistical significance to them. So we wanted to assign, in this case, a p-value to them. And so the p-value we assigned to this filament loop here was 0.011. And then I'm going to talk a little bit more about the voids in a moment. But in order to assign statistical significance, we used the persistence diagram and a technique that was developed by Fazy et al. In defining what they refer to as these confidence bands. So there's a way we can get a confidence band on the persistence diagram. And in this case, it's a 90% confidence band for the voids for the two homology group generators. So the points outside the band would be considered topological signal, and the blue points within the band would be considered topological noise. So points that ended up not having high persistence were ones that were, so the ones closer to the diagonal were considered noise, and the ones further away are signal. And so we were able to take their method of defining these confidence bands, and instead just having kind of a band, we were able to assign to each of the features a p-value. And so that's how we can get p-values assigned to these different structures. Okay, so then we did a little test also with this Voronoi foam data set where we basically simulated a data set where we knew that the center of the voids were. And then we applied our technique for using persistent homology and assigning p-values. And then we checked to see if the center of the voids that we found using persistent homology, if they were uniquely mapped to the voids that were present when we simulated the data set. And indeed, we did get the matching that we were hoping for. And then this table summarizes the p-values that were assigned to each of these structures. Okay, so as you can tell just with the confidence band here, not all of the features, not all of the voids end up having high statistical significance. Some actually have not very good significance. So we would kind of, if we were doing kind of appropriate hypothesis tests to decide if there's a void there, we might say there's not. Or rather, we'd say there's not evidence to suggest that there is a void present. I should be very careful with that. But then some of the p-values were quite small as well, like less than 1/1000. Okay, so then what we did is we wanted to look at how our persistent homology technique compares with some of the other methods. And in this Libeskind et al. 2018 paper, they actually did just that. So they had a particular cosmological simulation data set, this Gadget 2 dark matter only and body simulation. And so we used their data set, applied our persistent homology code, we call it SHU. And then, so this is just showing you what our technique found. But then we did a comparison between the techniques in their paper. So this is a slice of their simulation, and these top two in the center are showing the results of our method. So on the left, we just have all the voids that we found using SHU. And then next to it, we have the voids that were statistically significant that had p-values less than 0.1. And then we just look to see how it compared to these other techniques. You can see that all these methods have very different results where, so the red regions are, well, I should say the white regions are where the method says there's a void present. And so you can just see that there's just quite a variety. It's it's hard to say, right, with cosmological voids, what's the right answer, but it can be interesting just to see how the methods compare. Because some of these methods you can see were really designed to find where there's matter, and then everything else is void, while some of the others were maybe specifically defined to find the voids instead of just where there's not the matter. Okay, so that's just a kind of a brief overview of some things you can do with topological data analysis applying to the cosmic web. Now I just want to give a little bit of information about an exostatistics project, which is exoplanets and statistics. And so what we were trying to do with this project, and so I'm going to focus on this paper by Alan Davis that we had worked on. It was published in 2017. Our general broad goal is to find exoplanets, and specifically we want to find low mass exoplanets, even exo-Earths. And the issue is that stellar activity, such as the spot we see here, can cause problems. Some of those problems are, just maybe hiding a planetary signal, but perhaps worse, these sorts of activity can lead to also false detections because they can mimic planetary signals. So what I'm going to show today, which was one of the main priorities in this paper, was just to show that stellar activity can leave an imprint on the data. It leaves a different, sorry, to show that stellar activity leaves a different imprint on the data than a planet leaves, and in particular on the spectrum. Okay, so let's start with this. So if we look at exoplanet discoveries by year with the estimated mass on the vertical axis, we can see that as time goes on, we seem to be able to find lower and lower mass exoplanets. But more recently, there is a sort of kind of bottoming out, right? We have a few planets that have Earth mass less than 1, but not as many as we might expect if we thought this particular trend would continue from before 2010. And so what's going on here? Well, some of the improvements we saw over these years were improvements in the precision of the spectrographs, and those there continues to be improvement. Astronomers are constructing better and better, really amazing spectrographs that can get the precision down quite a bit, which I'll talk about in a second. But as that happens, we also find that activity becomes a bigger problem because the lower mass exoplanets have a much smaller signal, and so they're harder to find, especially amid any sort of problematic stellar activity. Okay, so I'm going to focus on the radial velocity method. And so the radial velocity method is the one where we look for a wobble in the star, suggesting that there's an object orbiting the host star. And we're looking then for the spectrum for red shifts and blue shifts across time. And here's an example of what we could end up getting in order to determine if a planet seems to be present in the data. So each spectrum, so imagine we have a collection we have a time series of spectra, and each spectrum then is turned into a one-number summary, and that one-number summary is the estimated RV. And then we plot the estimated RV across time, or maybe phase-fold, and just plot it across phase. And what we're looking for then is a particular shape for these curves, a sinusoid, suggesting that there's an object that's present. Okay, so this particular data set we see here is 51 Pegasi b, which was the first exoplanet discovered orbiting a sun-like star. This was from 1995, and it led to the Nobel Prize in Physics in 2019 by the two authors. And so we see here that there's a clear periodic signal, and that is, of course, what suggested the presence of the planet. If we look at the scale of the y-axis, we see it's in meters per second, and the semi-amplitude, so the radial velocity, is about 56 meters per second. Okay, but if we want to find Earth analogs, we're looking for signals that would be on the scale of like 9 centimeters per second. So that's going to be a much smaller signal that we want to find. Okay, so then what's the problem? I already had indicated that that stellar activity can lead to problems. This is so one of the major issues can be spots, because spots can lead to an apparent RV signal, because as the spot kind of orbits with or rotates with the star, it can the kind of flux balance of the stellar surface gets broken a bit, and so it can lead to like a blue shift red shift imprint, and that then could suggest a planet that's present when really it was just activity. Okay, so here's a little illustration of what can happen. So we could ask this question: is there a planet in these data, and if so, what's the radial velocity? And so this image was set up by Deborah Fisher, where she took the image from this particular Nature paper, and so in this Nature paper, they actually were saying that they've discovered a planet. It's quite convincing, right? It looks we have a sinusoid signal. It's the period is about 3.5 days. It persists across 2 different time windows, and so it was thought that this was a planetary discovery. But it turned out that a follow-up study, which you can read about in this particular paper, actually said that a star spot seems to be the more likely scenario rather than a planet. They looked at different kind of estimated RVs across sections of the spectrum. They differed, and they said if a planet was present, we'd see the same RV across the spectrum. They did some other things, but this just shows how activity can kind of fool us into thinking that a planet may be present, and so that's a problem. So what we were looking at is if we can disentangle stellar activity and Doppler shifts by looking actually at the spectrum instead of just focusing on the one number summary of the radial velocity. And so we carried out a test. So in this paper, we were just working with simulated data. We used what's called SOAP data from the Spot Oscillation and Planet 2.0 simulator by Xavier Demusque et al. It uses a quiet solar spectrum as its base, and then it allows you to add in activity of different types. And so we set up our simulation to have a star that rotates with a period of 25 days, and we had 1 spectrum per day. And then we added into our data a spot with different coverage areas. So we had 3 different data sets for spots. One had a 0.1% coverage area. One of the data sets had a spot with a 1%, and one had a 5%. And then we also considered a planet in a circular orbit with a semi-amplitude of 1, 10, and 50 meters per second. This is just an example of one of the SOAP spectrum. Okay, so then we for each set of these data, so for the case with a planet with 1 meter per second, and for a spot with the coverage area of 1%. So for each of those different sets, we looked at a principal component analysis of that collection of 25 spectra. And so this is just a kind of a 1-slide overview of PCA. So each point in our data set is representing, each point within this 3D space, which would actually be much higher dimension depending on how many wavelengths we have in our spectrum, is representing one of the time series spectra. And then the first principal component finds the direction of maximum variability. And the second principal component finds the direction, kind of the next direction with the next most variability in such a way that it's orthogonal to the first. And then we just continue on with as many principal components as we have spectra in this case. And then from that, we looked at a certain projection. And in this case, so just ignore the facula, the middle one. But what we looked at here is just the projection. So the first principal component kind kind of projected back onto this, the vector itself. So these are kind of the weightings of the principal component direction. And if you compare this top one, which has the principal components for the spot, and compare it to the planet, which is on the bottom, you can see that the imprint is actually different between the spot and the planet. If we just focus on this one absorption line here, you can see that the spot has this kind of positive PCA weights kind of in the just in the core of the line, while the wings have kind of an opposite variability, right? It's from positive to negative. While if we look at what's happening with the planet, we see that it's blue on one side and red on the other, right? Because that's what's happening with a planet. We see a Doppler shift going back and forth. And so the variability on each side ends up actually just being kind of opposite, but equal in some sense. Okay, so the takeaway here was that spots have a different PCA signature from planets. And then we did some additional experiments where we added noise and changed the resolution and tried to see how many principal components we could find before kind of noise overtakes it all. And from that, we considered a whole bunch of different resolutions and different signal to noise, and counted how many principal components we could find before noise overtakes it. And so we see the spot on the left. Ignore the facula for now. If you want to read about it, I just go. You can look up the paper. But so we have the spot and then the planet, and the coloring for each is just indicating how many principal components we had before noise overtakes it. And so we can see how, of course, as the resolution and signal to noise increases, we can uncover more principal components. And so for a spot, we can get up to 5 when we have the 5% spot. And then for the planet, we see that the most we uncover is 1. And so again, we see a difference between the spot and the planet, suggesting different signatures, different types of variability across the spectrum. So that was great. That was what we were hoping to show with our simulation study, and that that leads us to think that actually there's a lot more information in the spectrum that we could use to separate out the stellar activity from any real planetary Doppler shift. Okay, and so some of the newer spectrographs. The extreme precision radial velocity spectrographs are in development, so we're getting far better data. And this is one that one of my collaborators, Deborah Fisher, had built with her team. This is a group of us. This is Alan Davis. He is the author of the paper that I was just talking about. And this is the Express spectrograph. And you can just see, this is actually an example back from 2018, but you can see how the Express data, even just initially, now it's even better. Great examples you can find in these papers with just amazing data, but you can see the comparison between Express and some of the previous spectrograph observations. Okay, and I list here some other papers that you can look at if you're interested in this line of work. Some active projects people are working on with line level modeling and other robust methods for estimation, identifying activity sensitive lines. And then there are a number of great papers that use Gaussian process-based methods for kind of estimating or trying to separate out the RV due to a potential planet or planets and activity. Okay, so I'm just going to say actually a few words about some Bayesian methods, and in particular approximate Bayesian computation, and then I'll wrap up in just a minute or two. Okay, so this is a word cloud from a query on Bayesian in Astro papers from 2013 to 2018. And you can see that Bayesian methods have popped up in many different areas in astronomy. We see astroseismology, we see Jupiters, we see gravitational waves, AGN. Gosh, if you look closely, you'll just find a whole bunch of different types of kind of, I guess, different fields in astronomy that have used Bayesian methods. So there's also 3 textbooks that you may be interested in if you're either starting to work or work in astronomy and cosmology and use Bayesian methods. So these are some good references. And just a quick overview of ABC. So with Bayesian methods, what you are often seeking is a posterior distribution on the parameters. And the posterior distribution is something that's proportional to a likelihood function times prior distributions on the parameters. And once you have the posterior, though, you can do all sorts of different types of inference. You can do credible interval estimation, you can get point estimates, you can do hypothesis testing, etc. So getting the posterior, though, is one of the first steps before you can get into any subsequent analysis. But it does rely on you to specify a likelihood function. Approximate Bayesian computation says, well, what if you don't actually have a likelihood that you believe? But you feel like you can simulate the data quickly, and that's going to be a better approximation than any likelihood for modeling your forward or your data generating process. So that's where ABC is one option for taking a likelihood-free approach. And again, it's instead of a likelihood, you have a forward modeling simulator. And then there's there are a bunch of different algorithms that you can use to implement ABC. I will say, if you feel like you can write down a likelihood that's reasonable, you're gonna if you can write down a reasonable likelihood, you should do that. This is more cases where if you really feel like the likelihood is not a good approximation and there may be a bunch of other things happening in your data that you'd like to account for that you couldn't easily write down in a likelihood function, then ABC could be a good option for you. It also can just be fun to explore and see what happens if you add in different effects. Maybe you have observational limitations. Maybe there are strong dependencies. An example that I had worked on with some collaborators is for the stellar initial mass function, where if you want to add a more realistic, let's say, completeness function, you also maybe want to incorporate some aging effects and measurement error. But perhaps more importantly, trying to capture any sort of dependency that may be present due to the star formation process within the cluster. Maybe ABC could, a simulation model and ABC could capture what's going on there. Okay, so here are some ABC references if you're interested. And so that is what I wanted to cover today. So just a quick reminder, I gave you a little bit of background on astrostatistics. It's a growing field, especially as there's more and more large or complex astronomy data. We need more astrostatisticians to keep up with that demand. But astrostatistics also applies to small data. So if you don't have many observations, astrostat could also be useful. And then I talked a little bit about topological data analysis and persistent homology with the cosmic web, a little bit about exoplanet detection amid stellar activity, and then just very, very briefly about ABC and Bayesian methods. Okay, so I will go ahead and stop there. Thank you for your attention. And again, sorry for the delay at the beginning. All right, thank you.
Okay, Jessi, thank you very much for this great overview about astrostatistics, showing how powerful the techniques are, so allowing us to go from cosmology to exoplanets. So that was a really interesting overview. And also for all the reference and textbooks and meetings. And in particular, I attended one of the Penn State summer school in astrostatistics. So it's a great meeting. So I highly recommend to everyone who can attend it. So, and you were one of the professors in the edition I was there. So that was really nice. So if anyone has the opportunity, just please attend. It's a very intense and cool week.
Yeah, and this, as I said, this year it's virtual, so you can save on the travel expenses. And I know it's not always as fun to just sit at home in front of your computer, but you can at least get an overview of everything that's going on in the lectures. So
Exactly. So we have a few questions here in the chat. So if you have questions, please leave them on the chat. That I'll read them. So we start with these. There's a two-part comment, so I'll put them on the screen. So Luciano asked that when we implement algorithms in persistent homology, we use, I don't know how to say this correctly, check, não sei, I don't know.
I say check, yeah.
Okay, complex for underlying geometry. So the major disadvantage of this is that we have to check a larger number of intersections, and then he continues. So it's going to approximate this complex with Viatoris Rips type complex. So do you think this approximation could speed up the algorithms and simulations?
Yeah, I mean, so my understanding of how, I don't know if this is like universal with all the different persistent homology computational packages, but I think actually it is the RIPS complexes that tend to be used. If they're not being used, then I think at least in theory it should speed it up, or I should say, no, not even in theory. In theory, I think that they you may not think it would, but in practice, I think it actually does speed things up. Because if I remember correctly, and then I may not be, but I think they kind of scale similarly theoretically, but the RIPS implementation does end up being faster. But just to add on to this, yeah, it's not fast. Persistent homology, switching to RIPS maybe would speed things up if what you're using implements the check complexes, but I think it is generally a big problem. Now, one thing, so if you're working with point cloud data, like let's say you have a cosmological simulation, you have billions of points, it's let's just say we've tried running code on it with billions of points, and it I don't think even the computing clusters we've been using were able to handle it. So we tend to either have to downsample, or actually what we do is we take the point cloud data and we discretize it and turn it into a function, and then the grid resolution is it's washing out some features by not looking at the individual points. But if you know that the scale you're interested in is let's say a megaparsec, then you can make the grid with a megaparsec, and you still end up with a lot of just as you said, there's a lot of it's still going to be slow. Let's just put it that way, but it won't be as slow because it just depends on how many grid points you have. So it depends on the size of your simulation cube, and then the scale of your grid that will then instead correspond to the points. So each of your 3D grid kind of cubes would correspond to a point, like if you were doing a RIPS type complex. And so it still can be slow, but you can kind of get at least some speed up by considering a function instead, as long as you don't need a super high resolution. Does that make sense? Kind of like, is that?
For me, it does. Let's see.
Okay, well.
Let's see if Luciano come back.
Well, maybe I'll just make one other point. So I don't know if what kind of package they're using. I think what we have been implementing. So we use an R package called TDA, and it connects to. There's an option to use Dionysus or Goody or FAT, and I think we tend to use Dionysus, and I pretty sure that Dionysus would rely on a RIPS type complex. And I have not seen others using check. I'm sure they exist, or there may be some types of packages have that option. I have not explored all the different implementations carefully.
Okay, thanks. So, okay, Luciano posted here. So yeah, thank you. So
okay, great. Thanks.
So it made sense. So great.
Okay.
Well, now we have an interesting question here from Hélio. So he says that he has seen some criticism about using p-values as statistically meaningful. So what's your opinion on that?
Yeah, I mean, so that's the thing about p-values is in statistics, the history of the 0.05, which 0.05 was like the cutoff that if you're taking an intro stat course, you probably would learn 0.05, is the cutoff for p-values. Less than that, it's statistically significant. Greater than that, it's not. And that goes back to R.A. Fisher in some of his work suggesting that as a cutoff. I personally, so if I use p-values, I tend to just report the p-value, because that way anyone reading the paper can kind of in some ways pick their own cutoff. Like you might think, yeah, 0.01, that's not very small. Like I would not think that there is a cosmological void that's present. But if it was, 10 to the negative eighth, then I think that's more convincing. So if you just report the p-value, then it allows the individuals reading the paper to kind of, in some ways, pick their own cutoff. Now, sometimes it really does make sense to set a cutoff because of whatever you're doing. Maybe you're checking power, the power of the test. So I guess I don't have strong opinions about cutoffs. I would say, depending on the field and what's going on in your data, it can vary quite a bit, right? Because particle physicists would never use 0.01, right? I don't remember now. Is it 10 to the negative 10 that they require, or maybe even smaller? But if you work with social scientists where maybe they have survey data, suddenly, I mean, if you use a cutoff less than 0.05, you'll have no useful information because there's just so much noise in the data. Because survey data just tends to be, depending on the situation, can be quite messy. So I think it does end up being kind of field dependent as well. But at least if you just report the p-value without saying if it's statistically significant or not, people can kind of make their own judgment. And to some, if it ever comes to a point where a community has to decide what's an appropriate cutoff for this type of, let's say, experiment or this type of data, it would just have to be based on a consensus. But I'd say there's nothing magical about 0.01 or 0.05 or 10 to the negative 10. It's it really, right? It's a matter of what's convincing, and it might just be the case too that one experiment or one study with a small p-value is maybe it's kind of convincing, but the most convincing aspect of it is that someone else tries to run a similar study and just see if it's reproducible, if that result is reproducible, and that can then build a consensus of kind of support or evidence in favor of whatever one's looking at. So yeah, that's my, it's my 2 cents on it. There's also oh gosh, when was this from? 2015, 2016, the American Statistical Association put out a kind of a perspective on p-values. And I can't, let's just say there are 10 authors. I can't remember the exact number, but let's say there are 10 authors of, the top statisticians, and you get like 15 different perspectives on p-values, right? So everyone has their own perspective and then some. It's a very interesting read, and I would recommend it. But yeah, p-values are they're kind of a touchy subject in statistics too, generally. But they can be useful, right? It's just another kind of one number summary of an analysis, and so I don't think it's going to I don't think it should decide ultimately, if everyone in the field is going to believe something or not. But it can help or can contribute to providing evidence in favor of some conclusion.
Okay, thanks. So now we have a question from one of our students. So Marco, he says he's new in the field of astrostatistics. So he asks for some advice on what statistical methods do you think could improve the detection of really faint signals, like, for instance, gravitational waves?
Yeah, so I think from what some conferences or workshops that I've been involved in, I think that there have been some, maybe even I'd say some successes of using Bayesian methods for detection of really faint signals. I mean, in particular for gravitational waves. It's not a field that I work in, so I can't say too many details about gravitational waves in particular. But what can be this can be useful and also kind of problematic. But with Bayesian methods, you can specify if there's some expectation or additional kind of physical knowledge that you have with the Bayesian framework. You can often build those into your approach, which is useful as long as the physical knowledge is accurate. If it's not, then it doesn't help that much. But you can build that in, or if there's kind of if you do have prior information, like maybe the signal's faint, but you actually do have a sense of where you expect to find the signal, you can adjust priors to kind of focus on those regions. Now the issue with that is if you use a prior, let's say that that others really disagree with, or it's like maybe it's too narrow or too focused on what you think where you think the signal is, then suddenly your result it's not as convincing. But as more and more data become available, that can adjustments can be made to the framework. But that can work. In some ways this is related also to finding the detecting low mass exoplanets, right? Those are, you can think of as very faint or very small signals. And I mean, there's just a ton of work that's going on all over the world, a bunch of different groups trying to figure out how to uncover those sorts of signals. And so if there are known roadblocks, like with the exoplanets, the activity is kind of a known hindrance. You can start focusing on trying to understand the hindrance and then build those into an overall framework that's a matter of kind of detecting the signal, but also controlling for the hindrance. And so I don't know if that sort of idea applies to gravitational waves, but maybe that could be another way to go. So I had mentioned with the exoplanets, Gaussian process regression has been a tool that many have been using. So once you have your RV curve or RV data, trying to build this Gaussian process model that kind of accounts for an expected RV signal, but also tries to control for activity by using different stellar activity indicators like a bisector span or full width half max of the cross correlation function.
Okay, thanks. So as you mentioned exoplanets, so I have a question. So it's well known that the field of exoplanets and the results and the detections, they have lots of biases. So what are the main ways in which we can do relevant statistics taking into account these biases? What are the main tools that we can use right now?
So when you say bias, do you mean in terms of kind of like population level statistics, where because we know it's not like a random sample of exoplanets, right? Like many stars are targeted because they're expected to have exoplanets. Yeah. So I mean, that's hard because it's in some ways we don't know how biased the data are, right? Like we can say there's a bias because either astronomers are picking specific stars, or like with Kepler, it was focused on a particular region in the Milky Way. And so it's not like we could just take all of the exoplanets discovered and just take a random sample, because it's a random sample from a very biased sample. And so so trying to account for this sort of, I guess we could describe it as like a person or a team level selection bias is tricky. And I mean, one way one could at least try to work it out is if there were kind of known, I want to say like known cuts in the data, like maybe like like astronomers were seeking particular types of stars, and they were looking for particular periodic signals. Like you can, if there were certain decisions made within the pipeline of selecting the stars to seek, that would, you could try to build that in. Like that's where I start thinking like ABC could try to account for that sort of thing if there's somehow a good simulation model to use. But these sort of like unusual cuts to the data would need to somehow be known. I was going to say something else. Yeah. Okay. So yeah, I lost that train of thought, but yeah, it's I guess just more would have. Oh, this was what I was going to say. And this I don't think generally would fly, but having some way of publicizing or making aware non-detections would be useful, because the issue though with non-detections is that it doesn't actually mean that there's not an exoplanet present. It just means that for whatever instrument and amount of time was used for that particular star, one was not uncovered. But knowing that could also be helpful, like trying to have some way to source or make available planets or stars that were monitored and did not detect exoplanets, and then all the information that would be needed for that, right? The kind of what method was it? Transit? Was it radial velocity method? Or what was used to observe? What they would have expected they'd be able to discover, to leave room for, okay, so there still could be an exoplanet, but it would have to have certain characteristics. I don't know, that could lead to some help in that direction, but it's not going to be perfect. And it's it's just that's a really hard problem. I don't, it's one of those things where you could come up with techniques to try to mitigate it, maybe, but it's almost, you can frame it as a statistical problem, that's for sure, but it's also just a data limitation problem. Like if we could just monitor all the stars in the Milky Way and like using every instrument, that would be helpful.
Yeah, but, it would. Okay, Jessi, thanks. So, okay, Marco also thanks you for the answer about some ways, some methods that you mentioned. And Israel also puts here, so he has 4 books, but you mentioned this during your presentation, right? So maybe Israel could go back there. Oh, let me put here.
Yeah, can you still see my screen? Okay, great. Yeah, so these are some Bayesian books. And so I have this one, actually. Some of you may recognize the names, because Raphael and Emily, they're at least from Brazil, and I believe Raphael had said that that he was within your department. I'm not sure if Emily was too. But this book, I think, it's really nicely written, and they use R, JAGS, Python, and Stan, so all these different kind of computing environments. And then if you're very, very new and have no background, or I should say limited background on statistics, the textbook by Jogesh Babu and Eric Feigelson, where did I put that? That's here. This Modern Statistical Methods for Astronomy. So it uses R, but I think they describe the statistical methods quite well. It's actually, this would be the sort of book that one could use for a slightly more advanced intro to statistics, but it focuses on applications in astronomy. So this one could be a good one to look at. And these statistical challenges in modern astronomy textbooks these are more research oriented. They're based on talks at the different conferences. But this one would be, I think, a good intro. Also, just going to the summer school, like Luann was mentioning, so it's a good way to get a good, solid overview.
Great, Jessi. Thank you very much. So that brings us to the end of the Q&A and the talk. So I would like to thank you again very much for accepting the invitation and giving us this very nice overview of how powerful astrostatistics can be in many different fields. And before we, okay, Elio mentions here, so Rafael was an undergrad student
okay, that's
in Valongo.
Great.
And Israel also thanks you for the suggestions, and also says that he was very happy about the presentation.
Oh, thank you. Thanks for joining.
And before we end up, do you want to say anything else? Do you want to add anything else before we close up?
Yeah, just thank you for the great questions and for listening and for inviting me. I really enjoyed the interaction, so thank you.
Okay, everyone. So thank you again for attending this talk. Don't forget to subscribe to our YouTube channel so you can get reminders of the next talks. You can also check them on our webpage and our social media. And okay, before we close up, Luciano also is very happy about the talk.
Oh, thanks.
And okay, so be safe, take care, and I hope to see you all next week. Bye-bye.
Bye, thank you.